So the second example we did was introducing ramps, and our example here is a box is sitting on the top of a 40-degree ramp. So here's our picture of it. Maybe separate a diagram from words. And the thing that we are charged with doing is drawing the free body diagram of this object, okay? So we just have to analyze if this box is sitting, in your life you have experienced, if you put something on an incline, and we did this in lab, right, when we did motion on an incline, things fall down inclines. So if this thing is sitting, then that means that there must be some friction, right? So since it's just sitting there, we know that there must be some friction at play. So keep that in mind. So let's do that free body diagram. We have this. Remember, our mg always goes straight down to the center of the earth. And we're going like this, mg. And what we are changing now is we do have a normal force because it is on a surface, but remember the normal force is perpendicular to the surface. So in previous examples, the normal force would go straight up because it was on a flat surface, but in this case, our normal force has to be perpendicular, because that's what we define the normal force as, to the surface that the box is sitting on. Okay, so that's the first thing that we change. And when we are looking at this, okay, if there was no friction, we would assume that the motion, the velocity and acceleration of this object would be down the ramp, like parallel to the ramp. And remember that friction is in the opposite direction of motion or intended motion. So what that means for us is that friction is actually going this way. And I'm going to say it's static friction because it is not moving. And so it is not on what we would call our traditional X and Y plane. So the normal force is tilted up at an angle, and the friction force is parallel to the surface of the incline plane. So this is what our free body diagram would look like, but I'm just going to draw some of these vectors, forces, as we're looking at them on the diagram instead of the free body. Just because before, right, and all of the examples that we've been doing, we have been thinking of this, right, as what we would call perfectly horizontal as our X and vertical as our Y, right? But in XY plane, all that we care about is we have two lines that intersect that are perpendicular to each other. So as long as you still have perpendicular planes, you can call anything an XY. So we can actually tilt this XY plane, and instead of having them be what we would consider horizontal and vertical, let's get rid of that plane. Right, so that was our X. What we can do is we can change our ideas of what the X and Y plane are. And let's say that this is the X plane. The Y is perpendicular to it. So all we did was just tilt our perspective, right? So normally we look horizontal, but I'm tilting this idea of where my X and Y plane are, and I still have a 90-degree angle between the X and the Y. I'm just shifting this to make my life a little bit easier, or our lives a little bit easier. Okay, so we're saying that the force of friction is now along our x-axis, and the normal force is now along the y-axis. Okay, in our traditional, sorry, want to erase something a little bit. Sorry with the tapping as well. Oh, I can only go that far. Oh. Well, looks like we're going to erase and start over on that. Okay, so I just want to show you the difference, like why is it better to tilt our axis? So here's our mass. And we said here is mg going down. We have the normal force going perpendicular, and we have the force of friction going back this way. So if we go into our normal, what we would call x, and what we would call y, we see that only one of our forces, the mg, is along these axes. So we would have to break apart the force of friction and the normal force in order to get it into its x and y components. And also, I don't know much about this angle, right? And I don't know much about that angle. So we'd have to rely a lot on geometry in order to do that and break two vectors apart. If we change our perspective and call this the x direction and this the y direction, now we only have one force, the mg force, that is at an angle that we would have to break down. And when we're looking at this, technically, right, this line is, the x-axis is parallel to the to our plane, so technically this is an extension of our plane. And this angle that it's making with what we would call the ground is 40 degrees. Okay, so I'm just going to show a proof here of how we know, like, if we're trying to break mg into its components, what angle are we looking at when we are trying to find this angle, right? Because if I know that, right, this is the y component of mg, and this is the x component of mg, right? mgx, mgy, because again, I'm now calling this dotted blue line that is with the normal force, the y axis. I have an mg component that is going along that y-axis, and then the mgx is in the x direction, in the parallel to the surface. So I'm interested in finding this angle right here, because if I know that angle, then we can solve for the sides, right? Because we know that we can use sine and cosine. So what we can do to show this proof, I'll get rid of the components real quick. And right, there's our y component, or that's our y-axis. I'm gonna, technically this mg extends down towards the ground, and it would go like this, and it actually makes a right angle right here. Okay, so if I just made a right triangle with a 40 down here, of right here, this angle has to be 50 degrees. Okay, and then notice that right here, where the x and y meet, is 90 degrees. So that means that this angle that mg makes into the y, oh my goodness, with the y axis is 40 degrees. Okay, so what we just did there was show ourselves that if I know the angle of the incline, then I know that that is the angle that mg makes with our y-axis, what we have now defined as our y-axis. Okay, so we actually do know that angle, so we can solve for our components. I'm just going to redraw our free body diagram here. And I'm going to just scroll up here real quick to show, I'm going to do something that is helpful, I think. I'm going to draw our free body diagram like this one, where we're taking the components and putting them into into their respective X and Y areas. So we have our free body, we have our mg going down, we have our mg going down this way, we have our normal going, oh, it's severe, we have our normal going this way, and we have our friction, actually I forgot what color I used, yep, this one, going this way. And just a reminder for us, you don't have to draw this, but I'm just reminding us what our X and Y are. Okay, so if we do that, we have an mg y and an mg x. So if we redraw this free body diagram, what we have is mgy going this way, F normal going that way, mgx is going that way, and the force of friction is going this way. Okay, so that's what our free body diagram would look like. And if this thing is sitting on there, that means that there's no motion, right? This thing is sitting on the ramp. Not only is there friction, but there is no acceleration in the X or Y direction. Okay, so we can do some Newton laws stuff with this. We can think about our X and our Y, right? F net X is equal to mgx minus force of static friction. Let's actually get these colors in there so that we can see what's going on. Mgx minus force of friction. Okay, and then we have F net Y is equal to normal force minus the mgy component. And we just said that these are going to be equal to 0 because the acceleration is 0. So that tells us that mgx is equal to the force of friction, and normal force has to be equal to the mgy component. Okay, and we do know this angle is 40 degrees because that's what we proved up here. So whatever the angle of the incline is, that's the angle that our mg makes with the new y-axis. Okay, so we can say, right, if I know what mg is, and I don't know the mass, but that's okay, right? We know that we can at least set up our equation. Be careful here because our y is now adjacent to our angle. So for our y component, we're going to do mg cosine of 40. mgx is going to be mg sine of 40. So now we can plug these in. And mg sine 40 is equal to our force of friction. So if you knew what the mass was, then you can solve for the force of friction here. And then our normal force is going to be equal to the mg cosine of 40. Okay, so what we introduced here with ramps is this idea of just shifting our axis so we don't have to break down as many vectors, and also because the mg angle with our new defined y axis is the easiest of our angles to find. We don't have to do as many proofs with it. That is why we are shifting our perspective. So tilting and putting something on an angle, we have to tilt our perspective, but then it still just breaks down to x and y. Do your nets, add them together, do Newton's second law, and you can figure out some information about our substances, again, in chemistry class. We can figure out things about our objects, okay? Now, this is specific to this example, but the idea of our problem solving is what we use in all of our cases. So right now, in this example, because there is friction and it is not moving, we know that it is equal to mg sine 40. But there are times where you'll have a frictionless ramp, and then that changes our situation, but we still can look at free body diagrams to get our